So this one is easy. I already have some examples for you guys directly just lay it out. It's super simple, just a differential pair. I think 2 to 6 transistors, easy. And this one, I think it's not really hard. DAC, SAR, you already know how that works, what that looks like from the homework. And just this part. So there's a new circuit we need to cover in order to let you guys understand what's going on. So including a charge pump, including a circuit designed by Razavi. Do you know Razavi? So he has a couple of microelectronics textbooks considered as Bibles in this field. And he's a professor in UCLA and has been working in this area for over 35 years. If you search for his lectures online, it covers very fundamental circuits until advanced analog circuit design. This kind of thing. So he's just an analog expert in this field. So we borrowed, so these guys borrowed part of that, his circuit, and also the charge pump, which we're going to cover later this semester for this circuit. So the layout is pretty big. Anyway, so I'm not sure if we can do everything for this trip, because this is a 1 year long project for graduate students. If you see all the people who are doing this, they're PhDs, right? See if we can do part of it at least. Okay. For example, op-amp and track and hold, plus the SAR, whatever. We'll see. I think this can be a really good senior seminar project in the future. Let's see what you guys can do. I mean, if you guys already, towards the end of semester, you feel like you have a lot of spare time, which is unlikely, but just in case, if you want to do it, let's go ahead and do it. All right, so that's a goal. So you need a functioning D flip-flop. And the one I drew on the paper was not working properly. And because of this, right, let's take a look at the circuit. It's a D flip-flop, master and slave, I think, this one. So let's see why it's not working properly. What's the problem here? If, for example, if you, after you replace this one with a 3-input NAND gate, and you have a set on the top and reset at the bottom. So the issue is there's another input is still feeding signal to this NAND gate. For example, just imagine this is a 3-input NAND gate. Okay, so on the top you set it, but for this guy, you have 3 inputs. Right, so the one in the middle is not being controlled by the reset signal over here. If there's a reset signal, there are totally three inputs feeding into this NAND gate as the output. So it's not making sense, right? Let me make a snapshot. I know this is hard. So I have forgotten everything from logic, pretty much. All right. So if I have a signal, let's say it's a set, and there should be an inverter here, right? So setting this one, and then you need another inverter here to reset this guy. So for example, I'm trying to reset this. So when you are setting it, no problem. Why? It's definitive, because whenever you give S a 0, it's going to kill this NAND gate and give you a 1 to kill. But at that moment, whenever Q is 1, Q naught is not necessarily to be 0. Why is that? So for example, I have here 0, no problem, 1, right? Because the 0 is killing this NAND gate, giving a 1 as the output. And So this is when I'm trying to set it, I'm giving this guy a 1, right? Because I'm not resetting it. So this is supposed to be 1. Is that correct? Wait, 0, no, sorry, 0, 1. Oh, yeah, you need a 1 to set it. Yeah, all right. So you need a 1 here and 0 here to set it. Because 1 will be inverted, so get a 0. And it's going to kill this non-gate, I give you a 1, right? And this guy, because 1, 0 will be the code to set it. So this must be 0. And this is 1. And 1 is not affecting anything. It's just nothing. Just ignore this 1 here. And because this one will be fed back to here, so the 2 of the 3 inputs for this NAND gate are 2 1s. So these 2 1s are not affecting the result for this NAND gate. So the result will be dominated by this line. And can you control this line? No, because every falling edge is going to send whatever here to here, right? So that's why it's going to follow the D signal or invert it. All right, is that making sense? So that's why this works for setting. You just need a set signal, that's fine. If you also need a reset, which is the case we need for our SAR, okay? So this won't work because Q is not giving you a reliable 0 here. So are there any solutions? Just to this circuit, to this schematic? There must be a way to do it, but let's use a better one. I'll show you a. So when your stuff is not working, what you want to do? Just buy one. So just buy one, okay? This is what you can buy. It's from TI, which is a guru in making flip-flops. Why do you know one person? His name is Jack Kilby. Are you familiar with this name? JK flip-flop? So this guy invented integrated circuits 40, 50 years ago and won the Nobel Prize because of that. Worked in TI, Texas Instrument, back then. And so TI, right? TI is an expert making all these flip-flops. So this is one of the design, and you can directly buy from the market. So that's the entire schematic, no secret. You can directly use it, it's gonna work. And it's claimed that this is edge-triggered flip-flop, edge-triggered flip-flop, D flip-flop. Here's data, so it's a D flip-flop. And can we trust it? I mean, it looks like it's just 2 stages, or just 1 latch here. It's a edge-triggered or just level-triggered. How this can make it edge-triggered? I just want to verify it. Okay, let's verify this really quickly. It's a little bit different from the master-slave edge-triggered flip-flop we developed, but this is still an edge-triggered flip-flop. So by just looking at here, remember when we cover our SR latch, so this is the fundamental SR latch. A quick question: where is S? Where is R? Yeah, SR. Okay, it's SR latch. And so you know that whenever this guy is 1 and this is 0, are you setting or resetting this SR latch? Because this is the final stage, so it's going to dominate this output. Don't look at the whatever here yet, right? Just look at here. It's SR latch. So everything here is going to feed either a 1, 0, or 0, 1 to this final edge. So it's going to make this result flip or memorize the previous state. So it doesn't matter. Just look at this as our latch right now. If R is 1, S is 0, what is Q? So what does R mean? What does S mean? Yeah, 0, right? Because R is reset, S is set. So reset is being activated. So it's going to reset Q. Let's verify it. See if it's stable. How to verify this? Just see if it's stable. If it's keep flipping every cycle, then it's not stable. Then it's not going to work. But now let's take a look at it. So 0, because it's resetting the latch. So 0 will be fed back to here. Is this 1 going to be 1? After the time delay of the gates? Still 1. 1 being fed back to here, is that still 0? Yes. So stable. It's going to stay at 0, 1. So it's being reset. All right. So it's working. Now let's come back here, see if how this is edge triggered. If you are trying to make a judgment about this flip-flop, if it's a level triggered or only change the state at the rising edge, you want to start with the clock. So because only we hope this guy only being triggered at the rising edge. There's no inverters, so it should be a rising edge triggered. Okay, if this is 1, for example, this is 0. Right, we're just talking about reset. 1, 0. So this 0 will do what? If we label these ones, this is gate, the first stage and the first one. Okay, first stage, second one, gate. All right. So this 0 is going to do what? It's going to kill this NAND gate and give a 1 here. And 1 will be fed back to here and also here. This is being shorted together. All right. What else? 1 will be fed back to here because it's being shorted to here. And what's the signal here? 0. And come back to here. If clock, does that matter what the clock is? If we've got a 0 here, does that matter? No. So what is this? Still 1, stable. Okay. Then what's the conclusion by far? So 1, still 1 here. What's the clock? If the clock is having the state of 1, so it's going to be a 1 here as well. Is this affecting this result? No, still 0, stable. Back and forth, it's always stable. So what does that mean? If it's stable, what does that mean? It's not changing the state. After the rising edge, it holds. Right? Have I ever mentioned theta? No. What does that mean? Can be 0, can be 1. Can be anything. It's not affecting the result. Stable. What does that mean? It's edge triggered. Is that true? Is that making sense? After the edge, after there's a really short period of time, give you a 1, it's going to hold this state and not change. If your data is changing, it's not changing the result anymore because all this kills this and this signal kills this guy. Right? So it's holding, it's memorizing the previous state. Okay, this is just one case, right? So what if it's 0, 1? Wait. Another one. All right. R as, now which case we want to analyze this time? Set, right? Set. Okay. Let's verify this is setting Q, really quick. 0, kill it. 1, 1, 0, 0, 1, 1, 0. Set. Stable. So got a 0 here, got a 1 here. Okay. And 0 fed back to here, kill it. Got a 1. 1 being fed back to here, not affecting anything. But clock is so it's a 1, still 0. And 0 being fed back to here, kill it, got a 1, stable. And 1 being fed back to here, and then what? Huh? Yeah, data dependent, so whatever here will be data, right? Data bar, actually. But does that matter? No. Why? We are not using this line at all. It's not being sent to the output. It's just the first stage. And this is just being fed back to here. And it's going to oscillate, give you a little bit noise. Kickback, it's called kickback noise. So it's going to charge and discharge whenever the capacitor, whenever the gate oxide of the CMOS is being off. But however, because there is a little capacitance, it's just going to charge and discharge the capacitance. There will be a little tiny noise coming back, but tiny, like milliamps or something, or even lower. So it doesn't matter. What's going to happen to this gate? If this is 0, so it's going to kill this NAND gate and give you a 1 here and stable. Doesn't matter at all. So which means whatever you are setting and resetting this Q, or means like you have a 1, 0, 0, 1 here, it's not going to be affected by this data after the rising edge. So the rising edge will hold whatever the data used to be, and then it's going to hold in there. And you probably have a question. We have never talked about the data here, but how do you know it's a 0, 1, 1, 0 for these two lines? Yeah, we only need so for when we are using a latch, we only use 0, 1, 1, 0 as the valid states, right? That's the purpose of using latches. But when there are 1, 1s, it's a memory, it's holding the state. But we are not using that 1, 1 state, 1, 1 state over here for the flip-flop. Okay, so they need that to be initialized and to have a 1, 0, 0, 1 here to start with. So what's the difference from this one compared to the one we developed in the class? So we know this is rising edge triggered, right? So why is different? So you don't have to draw 4 stages to make a master slave, but they are using in different ways. For this one, it's synchronous. And positive. The reason is at the rising edge, it's going to sample D and hold it. It doesn't have to wait for the falling edge. But for the master slave, it samples at the first stage and then being transferred to the output whenever the next edge comes in. Right? Remember that? So if we run a really quick simulation, let's do one, and without we'll move to the Saturn reset pretty soon, but let's just look at the schematic without any Saturn reset. See, where is that one? D flip-flop TI, this guy. Okay, let me make some modifications here first. 5, 10.1. All right, let's see what's gonna happen. So that's the same schematic I just showed you on the paper. Okay. All right. Clock Q naught. Okay. So Q and Q naught are inverted. Looks great. And that's your clock. That's your data. Any comments? Anything? Any comments? No? Rising edge? And then what? Doesn't like the master slave DFF, the one we developed, which is asynchronous, because you have to wait for another edge to transfer the data from the intermediate stage to the final stage. You can see Q is pretty much copying D. So it samples, and directly being sent because you do not have another clock stage. So after you sample it, it's totally a combinational logic. So there's nothing to block it. It's going to directly be sent to the output. So whenever you sample it, it's going to send it to the output. But why it's not totally copying it? You know, there's a time delay here. And there's no time delay here. There's a time delay here. Compare these two signals. And there's a time delay here as well. Why? Yeah. So how can I modify it? Did everybody else get that point? Increase the clock what? Increase the clock frequency. Because your clock here is too fat. You see here why this guy is following this guy pretty much? Because this is just sampling here. So samples it and then send it to the output. But however, because the clock is too fat, for this guy, it sampled the 0 and sent the 0 to here, and wait until here to sample high, logic high, and then send it to the output. So if I increase the clock frequency, what would you expect? There will be less delay, right? It's going to pretty much copy. Let's try it. Let's make it 1 nano and 2.1 nano here. I shouldn't close all these panels. X D clock Q naught clock Q naught. Is that true? Is this doing the job for us? Yeah. Tiny, right? But is this working? Yeah. TI sells it, so it must work, right? All right. So now let's take a look at the Saturn reset schematic. Save it, doesn't matter. Here. All right, so that's a Saturn reset being added to the circuit, just based on whatever we had just now. Right. why this works. Can I verify it really quick? So let's see. If we have whatever is this on this line, a 0 here and a 1 here, it's supposed to do what? Set, right? Because this is the bar on the top. So 0 should activate that set. I hope. Let's see if this works. So if you have 0 here, then definitely 1 here, right? And 0 here, 0 here, and 1 here. Done. But what's the concern? What was the problem we had for our schematic? We can set it. We can set ours easily, but we cannot control Q naught. Was that the case in your schematic? So now let's see. Whenever Q is 1, apparently, because 0 here is a 1, let's see if Q is 0, which we hope it should be, right? Starting from where? 1, because when you are setting the D flip-flop, the code is 0, 1. So definitely have a 1 here, 1 here. It's shorted to here, so it's a 1 here. 1 here, 1 here. This is already a rising edge, it's already on the top. So it's 1, 1. No, it shouldn't be affected by the clock, right? Whenever you are setting and resetting or resetting, it doesn't matter what's a D, what's a clock. It should set and reset, definitely, right? So it doesn't matter. I mean, it can be 0, it can be 1. Let's just cross it out. Anything else? 1, shorted to here as a 1, and 1, right? The Q is not concerned because what we know is already a 1. Let's just look at this part. Do we have to assume 0, 1 or 1, 0? I think we do, right? Just like, let's take a look. For example, now the state is 0, 1. Okay, for example, now it's 0, 1. And 0 here will cancel this guy. So 0 here will kill this non-gate, so definitely got a 1 here. So I have 1, 1. And here's 1, 0. Okay. So this is a 0, 1 case. What if it's a 1, 0 case? See if that works. I didn't mention clock and data, right? So it's not being affected by clock and data. It's going to be 0, 1, 0. So for this one, let's assume we have the SR latch has a 1, 0 input at one moment, right? And now we are trying to reset it. So this should be 0. This should be 1. Okay. So 1, 1, 0, 0, kill it, 1, 1, 0. Are we done for reset? Do we have enough signals to reset it? Yeah. Because these are the 3 signals being connected to the output. And they are already done. 3 1s. What about here? 0, 3 zeros, 1. So you can expect the result. That's the same schematic we just saw. And I gave a set and reset a VDD. So it shouldn't do anything, right? Because it's not affecting the NAND gate. If I run a simulation, that's the first simulation I want to run. I probably need 6 plot pins this time. Let's add traces, data, clock, Q naught. Actually, just need a 4. Not that many. Yeah. It's too slow. Is this what you expect? Right? It's a very nice synchronous DFF rising edge trigger. It's the same, doing the same job as what we had just now, right? Because I have just put here to VDD, set and reset both to VDD. So it's not activating the set and reset function. So now let's delete this guy and ground it. What's going to happen? O zeros for Q. And O1s for Q naught. That's more important. Let's see if it's clean. A lot of noise. Let's change the scale, okay? So it's going to be 5 volts, 0 here. All right, so Q is 0, Q naught is 1, and very clean. So it's being reset, right? Similarly, if we put VD here and a ground here, run it. Same thing. I'm gonna just change the scale. Wait. Okay, so it's being set. Okay, so these little tiny noises will not trigger the logic change of the gates because the threshold voltages are normally 2.5. If it's way lower than 2.5, there's no concern at all. If it's close to 2.5, you want to redesign it. Make sense? So this is something, if you lay it out in your using the 500 nanometer technology and fabricate a chip, it's going to work. Something's going to work. Somebody is selling it. It's going to work. Okay. Any other questions for this homework? No. Okay. I will not go through the quiz because I have multiple lectures that I worked through this. It's the same type of problem. So let's move forward with semiconductor physics. Quick. Oh, I didn't show you that video. So from the ADC, the Columbia University's graduate students fabricated. So after the chip was received, they actually connected that ADC to their phone. So they just have their phone and play a music and plug in a little jack connector and cut the wire, have a plus and minus wires and being as an analog voltage input to the ADC, and they connect that signal to the ADC. They probably need an amplifier amplifier first, amplify it to the ADC's voltage range, and then sample it and digitize it using the ADC they fabricated. And because they do not have, I don't think they have any digital communication protocol that like I2C SPI these blocks or UART is too much work. I don't think they can get it done in a year. So they don't have these parts. What they have, you can imagine, will be what? So the analog in, imagine the SAR circuit I drew on the paper, remember? So there's one single wire to accept the analog input, right? And then the sample and hold, the comparator, the SAR, the DAC feedback, right? And where's the output? Right after the SAR, right? So in between SAR and DAC, there are 8 bits over there. We had a 4-bit, but imagine you have 8 bits. So this will be the digital output. And because you do not have a digital block to convert it into a serial output, like what you have used in microcontroller, right? So you have ADC, the output will be a one-line digital signal, just use the library like SPI, read. But here you do not have it, so probably don't want to sell it. Nobody will buy it. So it's going to be a parallel 8-bit digital output, right? So if you have a clock, the 8-bit digital signal of that analog voltage of that audio of the song, right? Whatever is the voltage, right? So whatever that point is, it's going to be sampled to the output and being converted to an 8-bit digital signal. So according to the clock, it's going to be like this. You have 8-bit parallel digital outputs. And how can I sample it and play it with a speaker? They actually did it. They have a speaker connect to the ADC, their ADC, and to amplify it to a speaker. So they need to amplify. After the 8-bit digital output appear as the output of the ADC, you do need a microcontroller, right? Do you need a microcontroller to do it, to read it? You do. So you need 8 lines to read that digital data and combine them to a digital signal, digital voltage, right? And then what? Think about it. 2 ways to do it. It can be a PWM, right? Or it can be an analog output, right? You can just convert it as convert that 8-bit input digital signal to analog voltage, which drives the speaker. That's why they can connect their ADC to the 2 wires from the phone and amplify it. Seems not necessary because if you unplug the jack connector, you can still play the song. But whatever is like, you can reduce the volume of your phone, make it probably not hearable, very small volume, and then it runs through the ADC, runs through my controller, and you can play it in the speaker. For other people who do not understand what's going on, but you know what's going on, since it runs through all the process to digitize the analog signal and then convert it into an analog signal and to a speaker, right? So that's a really fun project. Yeah, I think it's good for senior Sam. So we probably need a year to get everything done, but I think let's see what we can do this semester. Maybe at least the sample and hold and the SAR. Okay. All right. Let's see what I have. If I have a p-n junction like this, and definitely you're going to see a depletion region. And if I do not have any voltages being shorted to the two terminals of the p-n junction, then whenever the equilibrium is achieved, IS equals to ID. I want to verify, just want to make clear that you probably are confused. ID, definitely D means diffusion current, so that's a diffusion. Being driven by what? No, this is diffusion. So ID is diffusion current. What's the direction of the diffusion current? Yep, but it's driven by what? Concentration gradient. Is that correct? Because the holes are going this direction, and the same theory you learn in circuit 1. So the direction that the positive charges, or the holes here, right? The direction of the holes or the positive charges is the direction of the current. So that's ID, no problem. And when equilibrium is achieved, ID equals to IS. So IS, by name, is called the reverse saturation current. That's why it's S here. It's being dominated by the drift current. So it's literally the drift current, but name is reverse saturation current. Let me write it down. So IS here, for this case only, it's a reverse but here is dominated by the drift current, which is driven by what? Electric field, yes. So if I draw a let's don't draw it now. Let's look at the second case. Is that clear for this one? It's equilibrium because there's no bias voltage, no voltage being shorted to the diode. You know this is the diode, right? Okay. No voltage. The diode shouldn't have any current flow through it. It's equilibrium achieved as internally as equals to ID. They're cancel each other. So no current being delivered to the output. No current runs through it. But whenever you have a voltage to bias this p-n junction, so plus minus, right? Plus is shorted to P. This is called forward bias. Because P is being connected to P, N is being connected to N. And in this case, is your depletion region being narrower or wider? So this is your p-n junction, in which the diode is being forward biased. And you know this is the diode. If you have a higher potential here, it's going to flow a current through the diode, right? So will this depletion region be narrower or wider? And why? How do you intuitively understand it? So starting from here, okay, since you know whenever it's forward biased, current is going to flow. So how the current can flow through it? Because this depletion region is getting narrower. And when it's narrow enough, the electrons and the holes can tunnel through this layer in between and flow through the N terminal. So it's getting narrower. And when it's getting narrower, CB, so the capacitance, because there's a little depletion region. And you can imagine these are the two metal. These are not metal, but they are a kind of material, and in between there's a region. It can be considered as a dielectric material in the middle. And whenever you are driving and charging and discharging a diode, whenever you have an AC signal, you'll probably consider the capacitance or the parasitic capacitance inside the diode. Okay, there's some kind of capacitance inside because there's nothing in the middle, and you got a layer are changing, so it's actually have an effective capacitance appear at the two terminals. So whenever you have a narrower depletion region, CB, the capacitance here, will be larger or smaller? Larger, because C equals to what? I forgot. It's D A over D, right? And times this. Okay, so that's a dielectric constant of the material. It's not changing. And you're not changing the area, but only changing the D. So when D is falling, C actually is rising. Right? So the third case, C P is shorted to N, N is shorted to P, so this is called reverse biased. Reverse bias. I forgot one thing to mention here. So for this case, let's just come back really quickly. For this case, since in equilibrium, ID equals to IS, okay? What about here? Which is larger? I know they are not purely ID or IS. They can be contributed by the voltage source over here, but we define everything flow to the right as ID and everything flow to the left IS. So for here, which is larger? Which one's larger? Which current is larger? ID, of course, it's being forward biased, so a lot of current is going to flow in that direction. Look at a little IS. So ID is being contributed by what? In this case, the electric field plus the concentration gradient. What about IS? Only the electric field formed by the depletion region. So that's why it's tiny. Make sense? Great. Here, what about here? First, is the depletion region getting wider or narrower? No brainer, right? Wider, because this is narrower, it must be wider. Wider. And then CB, up, down. Down, decreasing, because C equals to epsilon A over D, right? When D is up, C is down. And ID and S, which is larger? So you have a diode, it's like a diode, and you give a positive potential on the right and negative potential on the left. It's not conducting any current, right? So what about ID and S, which is larger? Because all the current flow to the right is ID or IS. Current flows to the right is ID or IS. ID, which is larger, ID or IS? ID is being dominated, so in equilibrium, ID equals to IS. But here, since you have reverse biased, so it's trying to push the current to the left a little bit more. So actually IS will be larger, ID will be smaller. Okay, so that's why here it's called reverse saturation current. And if you draw the curve, there are several situations for the diode when you are looking at homework assignments or anywhere else. So for ideal diode, what an ideal diode looks like, right? And what about a ideal diode, but with a VB, the barrier voltage, which is a little voltage here, or it's called a threshold voltage, right? Or building voltage, or barrier voltage, or threshold voltage of the diode. It's ideal diode, no reverse breakdown, but with a VB, looks like this. So here's 0.7 volts. So a real diode is different. A real diode. Here's a real diode, and no reverse breakdown. Okay. It looks like this. Here, VB, threshold voltage. Here's I, here's V, being applied to the two terminals of the diode. So what is here? A quick question. What is this current? What is this current? When the voltage is negative, it's being reverse biased. Is that right? And there's a little current when it's reverse biased. What is that current? Yeah. Okay, we'll cover more on Monday. Have a good weekend.